In fact, it's not only nice, it's necessary. Because if we don't, in fact, account for the failure mechanism type, the polarity distribution of the signal, before we stack it in our Kirchhoff migration process, we will not stack to the right location. I'll mention that again in just a minute. So here is an example then of, let's say, of a dip slip event where it's up on one side and down on the other, positive on one side, negative of the other. Here's real data along two arms of a frac star, and here's several more arms of the frac star. And you'll notice that polarity flip as you cross the focal plane. So locating that polarity flip immediately starts to tell you where the focal plane is, and to the extent that you have a distribution of these arms and can pick several points of polarity flip, you now can map out the focal plane, the failure plane of that mechanism, which is really a significant piece of information. I was going to talk about up and down, doesn't matter. So here's one of Terry's famous photographs of a black shale up somewhere around this country. And I use this to illustrate...
Peter, if I can interrupt, you know that one well bore that went high relative to the others?
Yeah.
That one well bore was in that stuff.
I didn't... no, don't tell me. I don't want to know that.
Yeah, no, you don't.
Because if I don't know it, I don't have to answer that question to anybody else either.
That's right.
When next time someone asks it, I'll put up this slide and I'll say it was in that.
Yeah.
And they'll say, wow, that was shallow. All right, so we have this J1 and J2 set that all of you here are very familiar with. And the cartoon here represents a horizontal well drilled perpendicular to the direction of maximum horizontal stress, as you would. And the illustration here is only diagrammatic, and it's to point out that in the old days, if we had these hypocenters going out as a series of dots on either side of these wells, the best interpretation of that set of points would have been to say that I had a tensile crack created perpendicular to the wellbore, growing, propagating in the direction of maximum horizontal stress, parting those rocks like the Red Sea, creating a conduit of certain length, width, and height that I could then calculate, and from that calculate how much I was going to get out of this reservoir. In fact, when you do the focal mechanisms on these events in today's data, what you find is that more likely you've got strike-slip failure on echelon on the J1 and the J2s heading out from the well, a completely different failure mechanism, a completely different model for how that reservoir is going to produce. So knowing these mechanisms is important. Here's another example, this now from the Barnett Shale. And as you look at this treatment and you see all of these hypocenters here, it's clear that there's something different going on here than there was here. And in fact, we didn't get very good frac and very good production back from that portion of the wells, even though the treatment of every stage was identical in terms of pressures, volumes, proppant program, whatever. And when we analyzed these events, we found that the events of this type were more dip slip and had a B value of about 2. And B value of 2 means that it's weighted towards the smaller events. B values that are above 1 typically are thought to represent failure in areas where there's low stress anisotropy, normal faulting, new faults being created perhaps. Whereas in here, the events were strike slip, had a B value of 1, more consistent, that means more large events, and consistent with the worldwide distribution of movement along existing faults and fractures. So what we probably have then here is that we fracked into an existing fault, and that fault moved and stole all of our frac fluid and frac energy. Really critical stuff to start telling the reservoir engineer and the completions engineer, and certainly much more so than, oh yeah, you did a really good job here, but we don't know why it didn't work over here. It just didn't work. So that's the kind of stuff we're moving to. Every one of these events is no longer an event, it's a beach ball. And that kind of makes it fun. Fracking is just a day at the beach. But we really want to go beyond beach balls. If we recognize that these failure mechanisms have a plane and a sense of direction and a magnitude, then we ought to be able to replace the beach balls with little elements, little discrete fracture network elements, where the size is proportional to the magnitude of the event. The direction isn't the direction found by joining dot to dot, but the direction is the direction consistent with the failure mechanism that we've mapped. And the sense of motion is also determined from that failure mechanism: strike, dip, and rake. And we can do that and then get away from making the stimulated reservoir volume calculations simply being a shrink wrap around the outer extent of these beach balls, actually integrating up the surface area of the fracs that have been created, because that's the sort, it's from those surface areas that the hydrocarbons escape. So that leads us to a workflow where we start with our ball, with the dots, determine them first, then the beach balls. We come up with a geocellular volume. We populate that geocellular volume, 6 minutes, populate that geocellular volume with a magnitude of fracking estimate based on the size of the events accumulated in each element of that finite element model of the Earth that we've created there. Then perhaps constrain some of the fracture directions with other kinds of information, geophysics, downhole, FMI logs, whatever, and end up coming up with a permeability volume that we can feed into a reservoir simulation. Moving all the way from geophysics into something that the reservoir engineer wants. So how would this manifest itself in a real project? Here is a well from the Bakken, the Tracker Fritz well in the southern end of the Williston Basin. And in this work, we decided to test two hypotheses for different fracture sets that had been created by this frac operation. One of them where we constrained the fracture direction to match only the failure mechanisms that we saw in the well itself. The other to allow for some secondary fracture directions based on an FMI log and the wellbore breakout that was seen in a well nearby. So we come up with different models. We have to have some way of testing which model is right. We create permeability models of these in order to test this through history matching. That is, running simulations of the different models and comparing it to the actual fluids that came out of the well. Model on the left being the frac-only data, model on the right being frac plus FMI data. The permeability is a little higher in the fracs over here, but a smaller area affected by the frac operation. When we ran the two scenarios through the simulator, you have the one on the left being the frac-only data, the one on the right being the frac plus the FMI data. It's a 50-year prediction of the water and the gas and the oil production, water, gas, and oil production that would come from those two different models compared to what was actually produced in the first 2 years. That's the blue coloration, blue, red, and green coloration over the first 24 months. Now, these are significantly different. There's 16% more oil recovered by the first model, the model on the left, versus the model on the right. There's also a heck of a lot more water. And we all know that this water has to be disposed of. It can't be just dumped in the river. So that's an expense. And here there's an economic decision, or there's an economic imperative being expressed here. Now it does appear to me, I'm no expert, it does appear to me though that this model, which predicted we'd already produced almost all the water we're ever going to, might be a little optimistic. Although, perhaps we have drained the water off and we're only going to get the hydrocarbons. But what this is really telling us, in some sense, is that we're more effectively draining all of the fluids from a smaller area in this model than we are in this one. And that's what you see in this pressure differential. You see that in this one we're really concentrating where the pressure drawdown is to the center, right near the well, as opposed to this one, which is reaching out farther into the hinterland. And hence, is accumulating less efficiently the fluids that are around the well. Anyway, I don't purport that that is the end of that story and the work continues on that model. I merely show it to suggest that we've gone a long way in the value proposition of microseismic monitoring from simply dots in the box all the way to start to address the reservoir engineer's real questions. Engineers are only interested in really one thing. On a well-by-well basis, they want to get more grease from each well at less cost. And they want to be able to predict how much they're going to get so that they can know how much to spend on the next well. So we are now moving away from dots in the box to a much more integrated approach to characterizing the reservoir from the microseismic data, realizing that these are prima facie data that provide knowledge about the reservoir. There's a lot of effort going into integrating the microseismic data, not just in interpreting it on its own, but to integrate it with all the other kinds of data that we have, the geophysics, the geology, the world stress map, the FMI logs, all of those other things. It's exciting work, and it remains really to be done yet. This project I told you about for Whiting's oil field, the Sanish oil field, where we've monitored close to 2,500 frac stages in the last year. We've been interpreting that data on a one well by well basis. Think of the opportunity to take 2,500 frac stages and look for the large statistical trends in correlating production against the different sorts of treatments that they did in each well and how that's expressed itself both microseismically and in the production since then. I think there's probably 5 or 6 PhDs just in that data set alone, because the textbook on how to do all of this work still has yet to be written. And at any rate, we're moving, as I said, away from the dots in the box into answering what are the real questions in the reservoir. What is the optimum well deviation and placement? What should the spacing be? What am I really going to get out of those wells in the long term? Because no one today, except Terry, can tell you what's going to come out of the Marcellus in the long term. What are my infill drilling opportunities? And when is it time to start refracking these wells? Because the thought now is that almost every one of these wells will be refracked over time. And with that, I think I have one little more whiz-bang movie, again of a Marcellus well. It is a range well. The 3D data are data provided by geokinetics. It's got some holes in it because I guess there were some coal deposits nearby and they lost data into the coal mines. But this is, in fact, in time, but to scale. No, it's in depth, but to scale. And it shows you where the treatment of this well actually occurred relative to the seismic data. And it's a start towards the process we're heading towards of being able to integrate these data into everything else we know. And with that, I'm done. If there were... I'll push them 5 minutes for questions and then we're out of here. 5 minutes for questions.
Sure.
Don't worry about him. He works for me.